So now that all the Terrence Howard hoopla has kind of settled down, I think it's a good idea to get back to doing something a little more interesting. And so a few months ago, many months ago now, I think I put up a little video. This was a teaser video called Sound Fields Radiated by Simple Sources. Okay, so this is a website that I found, and I really found this very interesting as it seems to relate to a lot of the other things that I've been talking about and showing you on my YouTube channel. So now that all the Terrence Howard hoopla has kind of settled down, I think it's a good idea to get back to doing something a little more interesting. And so a few months ago, many months ago now, I think I put up a little video. This was a teaser video called Sound Fields Radiated by Simple Sources. Okay, so this is a website that I found, and I really found this very interesting as it seems to relate to a lot of the other things that I've been talking about and showing you on my YouTube channel. So here is the website. It is called Acoustics and Vibration Animations, okay, by Daniel A. Russell in graduate program in acoustics in Pennsylvania State University. Okay, so I'm not sure how old this is. Let's say, oh, this is August 23rd, 2001. So this has been around for a while. Okay, so this is Sound Fields Radiated by Simple Sources. Okay, so the first one here, they talk about radiation from a monopole source. And so I will read this for you. It says a monopole is a source which radiates sound equally well in all directions. The simplest example of a monopole source would be a sphere whose radius alternately expands and contracts sinusoidally. So basically it'd be kind of in and out. It would be almost like a breath. I think they actually do refer to this as the breath modality. And so when you have a sphere and it's contracting and expanding in and out in a periodic pattern, this would be a monopole. And so the monopole source creates a sound wave by alternately introducing and removing the fluid in the surrounding area. Of course, the fluid is the air. So a boxed loudspeaker at low frequencies acts as a monopole. The directivity pattern for the monopole source is shown in the figure on the right. Okay, so this is what that looks like up close. You can see that you've got the angles being shown here. You've got these radiative lines and the angles, and you have these concentric circles that show the decibels, I guess the power near the source and then far away from the source. Okay, so this is the animation on the left here is what the sound wave looks like in the medium. Okay, so this is what the sound wave would look like in the medium for a simple source that is expanding and contracting. If you look closely in the middle here, you can see that the little dots are sort of going in and out. So the dots are moving longitudinally, but also radially around the circle. Okay, so this would be referred to as a monopole source. Okay, so then they do radiation from a dipole source. Okay, so a dipole source consists of two monopole sources of equal strength but opposite phase and separated by a small distance compared with the wavelength of the sound. While one source expands, the other source contracts, so they're in opposite phase. The result is that the fluid, the air, near the two sources sloshes back and forth to produce a sound. The sphere, which oscillates back and forth, acts as a dipole source, as does an unboxed loudspeaker. While it is in front pushing outwards, the back is sucking in. Okay, so a loudspeaker not in a box acts as a dipole source. Okay, a dipole source does not radiate sound in all directions equally. The directivity pattern shown at the right here kind of looks like a figure 8. And there are two regions where the sound is radiated very well, here and here. And there are two regions where the sound cancels out, and that would be here and here. Okay, so the animated GIF at the left shows the pressure field. So this is a pressure field, shows the pressure field by the dipole source. At the center of the pressure field, you can see a sloshing back and forth caused by the dipole motion. So you can kind of see here it is sloshing back and forth because these two dipole sources are not in phase, they are out of phase. Okay, the regions where the sound is canceled out show up along the vertical axis, and the grid motion is almost zero. The motion of the particles is almost zero in this region. Furthermore, the wavefronts expanding to the right and left are 180 degrees out of phase. So these wavefronts are not in phase, and that's why they don't make kind of perfect circles like this one does here. They are out of phase, and so when there's a peak here, there's a trough here, and when there's a peak here, there's a trough on this side here. Okay, so this is what happens when you have two radiative sources that are radiating out of phase with each other. Okay, and I'm just going to show one more case here. This is the radiation from a lateral quadrupole. Okay, so here we have two radiative sources this way that are one phase, and two radiative sources sort of vertically here, and they are the opposite phase of the ones horizontally here. So it says, if two opposite phase monopoles make up a dipole, then two opposite dipoles make up a quadrupole source. In a lateral quadrupole arrangement like we have here, the two dipoles do not lie along the same line. The four monopoles with alternating phase at the corners of the square. So you have phase A, phase B, phase A, and phase B going around the circle, going around the angles, okay? The directivity pattern for the lateral quadrupole looks like a cloverleaf pattern, like a four-leaf clover. Sound is radiated well in front of each monopole source, but the sound is canceled out at points equidistant from the adjacent opposite monopoles. Okay, so the animated GIF on the left shows the pressure field produced by a lateral quadrupole source, so four sources that where two are in phase and two are out of phase, or two have phase A and two have the opposite phase B. Okay, so at the center, the pressure field, you can see the quadrupole motion as the particles alternate motion in the horizontal and vertical direction. So if you look closely in the middle here, you're going to see sort of pushing out here, then pushing out here, then pushing out here, then pushing out here. Okay, so the regions where the sound is canceled out show up along the diagonals in this configuration, where the grid motion is almost zero. So the grid motion is almost zero. The particles in the medium are not moving in these regions, and they are moving in these regions. So in the destructive interference, the particles are not moving, and in the constructive interference, the particles are in motion, okay? And so furthermore, there's a 180 degree phase difference between the horizontal and vertical wave fronts. So now this wave front is the same as this wave front, or in phase. So these wave fronts at the top here are in phase with the ones at the bottom, and the ones on the right are in phase with the ones on the left. But these are, the one on the left is out of phase with the one on the top and the bottom. And so this is the radiation from a lateral quadrupole source. Okay, so we've got the monopole, which is the trivial situation where you just have one source and you just get your wave, you get your pressure wave radiating away from the source. And then you have the dipole source, where you have two sources that are out of phase that are close to each other, and it creates this pattern here. And then we have the quadrupole source where you get this pattern here. Okay, so where have we seen this before? We've seen this before. I've shown you these patterns before. So where have we seen this before? So the first thing I want to point out is how much these patterns look like the orbitals, electron orbitals of the hydrogen atom. Okay, so the 1s, this looks a lot like the 1s orbital, and this one looks a lot like this 2p orbital, and this one looks a lot like the 3d xy orbital. Okay, and so this is, I thought it was really interesting at how we were able to produce, the electron orbital patterns using sound waves in a medium, using oscillating spheres that are either in phase or out of phase with each other. We are able to produce these patterns. Okay, so the other place that we've seen where we've seen these patterns is in the isopotentials of the magnetic field. Okay, so the isopotentials of the magnetic field also produce these patterns. Okay, so you could imagine that the magnetic field, so in the case of the magnetic field, we've got the monopole, not the monopole, but when you look at a magnet from just looking at one pole, you get the isopotentials, and the isopotentials create the same pattern as the monopole of the sound wave source that is oscillating in and out, as in the in breathing mode, I think they call it. Okay, so a dipole of a magnet. So let's say this is the North Pole and this is the South Pole. When you plot the isopotentials, now the isopotentials are the potential. Okay, the isopotentials are not showing the vector of the magnetic field. It is showing the potential. So and if, when I use a Hall sensor to measure the potential, I'm going to get a measurement, say, in voltage. And so if I use a voltmeter to read the value of a Hall sensor, and I place a Hall sensor near a magnet, I'm going to produce these isopotentials. These isopotentials are equal potential line curves, and so anywhere along this curve here is going to be of equal potential. And so, of course, you get the similar pattern with the orbitals, with the electron orbitals and the hydrogen atom in the 2p orbital. And you get the same pattern when you have two dipoles that are oscillating out of phase and producing the interference pattern, okay, that we see right here. So this interference pattern, this dipole source where you have a source that's two sources that are out of phase with each other, it creates this pressure field where you have no pressure, you have no motion of the particles producing pressure in these regions here, and you have, say, the highest pressure in these directions here. Okay, so I think it was really interesting that these sound sources that are in phase or out of phase produce the same patterns as the magnetic field lines. Actually, I'm going to switch to this one here, because in this image here, this one is not oriented the same way as this one. So if I show this pattern here, you'll see that this one is oriented the same as here. So for the quadrupole, you've got two sound sources that are out of phase with each other in this pattern here. So you have two, you have a, let's call it a white positive and black negative. So you have positive, positive, negative, negative. And let's call, this is a magnetic field, let's call yellow positive and blue negative. You have positive, positive, negative, negative. and you get a similar pattern to what you get with the sound sources. And so this makes me wonder if there isn't some mechanism, some similar mechanism for all of these three things. So this is the domain of the atom. These are the electron orbitals produced that were, that are calculated using the Schrodinger equation. And this is the sound pressure waves, pressure, I guess you'd call them pressure isopotentials. These are pressure potentials produced by the sound sources in this experiment here, and the isopotentials of the magnet. So it just makes me wonder if there isn't some mechanism that is common to all three of these domains. Okay, this is the domain of the atom, this is the domain of the magnet, and this is the domain of sound waves. So it turns out that all of these things actually do have something in common, and this is in the domain of spherical harmonics. Okay, so spherical harmonics can be used to generate all these patterns. And so let's see if I can get this up here. So here is a visual representation of the first few real spherical harmonics, and of course these are exactly the what we're seeing in these images. Okay, this is exactly what we're seeing. These spherical harmonics are, for all intents and purposes, these values here. So these figures here. So all of these figures can be reproduced using spherical harmonics. Okay, so here are the some representations of the spherical harmonics. You can find this on Wikipedia. Okay, these are visual representations of the first few spherical harmonics. The blue portions represent regions where the function is positive, and the yellow portions represent regions where the function is negative. And here they're talking about the wave function. Okay, so the positive values for the function would correspond to, let's say, in the sound wave, in the sound resonance situation. So positive would refer to one phase, and the negative would be the opposite phase. So if the two sound sources are so this would be phase A and phase B, where A and B are out of phase with each other, 180 degrees out of phase with each other. Okay, so basically the spherical harmonics and the wave function that they use to generate the atomic orbitals for the hydrogen atom, and the isopotentials for generating the magnetic field isopotential diagrams, which we show here, are basically all based on the same math. Okay, so there is a correlation between all these things, and that has to do with spherical harmonics. And so I thought this was really interesting, and I think it's really important that we pay attention to this, because in the fractal paradigm, what I'm trying to do is I'm trying to find sort of similarities of different things at different scales, and try and bring them all together into sort of one line of thinking. And so in the domain of the atom, so what I want to say is the atom is a magnet, right? And the magnet is an atom. So I want to kind of bring all of these concepts together, and this seems to be a good way to bring all of these things together. And so you could imagine that maybe, what is a magnetic field? What is this? What are these isopotentials? Well, it could be that the positive and negative, or the North Pole and the South Pole, are radiating into a medium such as the ether. Okay, these could be spherical oscillators that are radiating into the medium called the ether. And that it could explain why we get the same patterns as aspherical oscillators radiating into a medium called air. So interestingly, and maybe not coincidentally, Ionel Dinu recently produced another paper which he calls the Fundamentals of a Theory of Ether Part 4, the mechanical origin of the electrostatic force, the nature of the electric field, radio waves and light, a solution to the wave-particle duality, the propagation of light in channels, and helping Millikan explain the photoelectric effect. Okay, so what I'm going to do is I'm just going to read the abstract to you, and then you'll see why I am bringing this up right now. Okay, so this work is further development of the theory that explains electrostatic attractions and repulsions by the molecular vibration of objects acting on one another through a liquid ether that fills the vacuum and the inner atomic spaces of substances. The 2,000-year-old problem of a mechanical explanation of the laws of electrostatics is answered by the behavior of coupled oscillators. So the physical origin of the electric field is that of a to and fro motion of the ether, just what I was just analogous to these sound waves, okay, these spherical oscillators that are, expanding and contracting, okay. Light and radio waves are shown to be longitudinal waves consisting of to and fro motions of the ether along the direction of wave propagation, which makes them essentially electric waves. Corroboration with results from previous work leads to the conclusion that the complete nature of light and radio waves is that from electrogravitational waves. The 100-year-old problem of photoelectric effect and the wave-particle duality are solved by uncovering the direct link between voltage and frequency of vibration, by a new interpretation of de Broglie's equation, and by advancing new theory of light propagation in channels. Okay, so I'm just going to read in a few pages down. I just want to show you this figure here, and I just want to read what he said here. He basically said, noteworthy in this respect are the recent works that start from de Broglie's original proposal of two-dimensional stationary electronic wave in an atom and take it to a logical and natural three-dimensional representation, leading to atomic vibration modes with different frequencies, while the shape of the vibrating atom in the spherical geometry resembles strikingly the atomic orbitals obtained by quantum mechanics. Okay, so Ionel Dinu is coming to the same realization that I came to from visualizing these three scenarios: the atom, the magnetic isopotentials, and this new thing that I found that is able to reproduce these patterns using sound sources. So I think this paper is worth a read. Ionel Dinu, of course, I did some work with him earlier on the electric wave, and so this is something new from him that I think is worth a read. Okay, so I will leave a link to this in the description, and I think this is an interesting piece of the puzzle. As you know, I like to collect puzzle pieces, and this is an interesting piece of the puzzle, and this of course is a very interesting piece of the puzzle, that spherical harmonics seem to be the common theme amongst these different scenarios. Okay, so I'm going to leave it at that, and I am way behind in making videos. I have started I started putting together many videos that I never finished because I get sidetracked with other things like, Terrence Howard and other distractions, and so hopefully I can get a little more focused and get some more videos out there. But I thought this one was really important, and so I really wanted to get this one out today. And so, yep, I'm going to leave it at that, and I hope you guys have a great week, and I'll be back.